find that there were addresses that were written by the bootloader that were not anywhere in the table. And I can't tell you whether that's a documentation issue or if that's a bug in the bootloader. But there are semantics that are not necessarily being enforced. And we could, if we just started understanding, like seeing these regions of memory as objects for a policy in which we can follow. We don't have to necessarily have like runtime enforcement of it, but it would be helpful while testing to have it. If we can have like the hardware support to do runtime, all the better. And yes, you can use page tables if you're, if that's enabled. There's ways to do this, and I will talk. We have some prototype that uses page tables that enforce this type of region-based access control. So during bootloading, well, I've gone over a lot of this, but the memory map and the address space may change multiple times, so you will see phases of different address regions being okay to write to, or being read-only, or containing nothing, or not even being mapped to any backend storage or registers. Then, memory will be initialized, stacks might be moved, or the stack might be moved. I've seen it moved 5 times for the particular bootloader I studied. It just had to dance around itself until it got enough RAM so it can spread out and not move its stack anymore. And so execution can be divided into substages by how the memory, or how the address space is intended to be used, how the regions are intended to be used. Once the stack changes location, you might want to say, well, this is a new substage. I'm going to look, the stack is over here now. There's just many different things that you can think about when you're thinking about policy, regions as types as policy. And so when I was thinking about substages for a bootloader, or for a loader specifically, when I wanted to write a policy based on regions, I thought, well, the major things a bootloader does as it's executing is it's preparing, loading, patching, linking some region of memory to be used by a future substage, by which I mean it could be where the image for the target that's going to be loaded is. It could be it's setting up, it's zeroing out a region of memory for the BSS for data that is assumed to be zeroed out. Or it could be performing internal bookkeeping, and there's a lot of internal bookkeeping in loaders. They need to, keep track of their progress. They need to have pointers to all the drivers and remember all of the devices that it already found and initialized. And so these are sort of the major stages: bookkeeping, preparing a future substage, copying to a future substage, and I forget. I wrote a policy, and I'm not really talking so closely about the policy. Oh, I wrote it here. So substages of the bootloader, I classified as either loading the future substage region, so copying, say, big chunks of data into there, patching, such as doing small little address patches, doing little fix-ups, or bookkeeping, and that's when the bootloader or loader is kind of doing stuff to keep track of where it is. And then during each of these substages, I thought to divide the regions into, code, which should never be written. Registers, I just decided to kind of make its own thing. You can say maybe if it's bookkeeping, or maybe if it's loading and patching, you can say no writing to any registers. Bookkeeping stage, so if it's in the bookkeeping stage, you can allow it to write to bookkeeping data. But if it's loading or patching, you can say, hey, no writing to bookkeeping data. And then, a region that's not quite ready yet to be used, but to be prepared. So a future substage image region, another tag to classify it. So of course everyone wants to ask me oh, did you find any, ODE in U-Boot? Well, so every single device has a way different build. U-Boot is just a big pile of code that is compiled down, to something, and a lot of code is not shared necessarily between devices. But the big thing with this particular device, this this development board, the BBxM, is it reads the image from the storage, from the FAT file system. From that, it will figure out where the header of it lies in memory. And using that header, it will read, well, using the, this particular pointer was where to copy the header into memory, and it will read that chunk of the file that has like the header information for this binary into memory. And from there, it will look at this header that it just loaded, copied straight off the file to memory, and parse it. And then, after that, this particular variable I circled, SPL image load adder, that is directly copied from the header. So the binary can say, I live at like on top of all these registers, memory map.io, and it will just read, you know, bytes into that address. So it will just copy things in there, and then like you have undefined behavior because you're just writing whatever. I mean, you could probably define it better. But so how trustworthy is it? Well, like how much do you trust the image is loading? But also you really have no choice to trust it. This particular boot environment is not meant to be like locked down or anything. But there is this there's often a trust in what you're loading is kind of telling you what it needs, where it should be loaded, or how big it is. And it's up to the bootloader to know if that interferes with anything it already has set up in memory. And like in this case, it clearly doesn't. But if we start thinking of regions as typed objects, typing them, we could write policy that works on that level. I mean, I can't imagine putting little types in here, you know, programming language that somehow prevents, you know, the region of memory with registers to be overridden by this particular thing. You have to really do, you know, checking of addresses and so forth. So this is where I just speak a little of some of my thesis work. I called it region-based write access control, and I said write, the word write a lot. It could be any memory operation, but I focused on writes in this thesis. And then, so the components of doing a policy based on regions of objects, regions are types, are the substages, the distinct phases of execution, and the memory regions themselves, and how they're expected to be used during that particular substage. And I already showed you this, but when you start thinking about software in this way, you start thinking in the bigger picture of policies. Like during this, you know, it jumps into this piece of code initially, and I know it's going to start off with bookkeeping. Therefore, it should not write to, you know, these particular areas of memory that may not have any backend store, or may have the code itself that's being executed. So there's like that phase, and then suddenly it's, you know, it enables some external memory, and it has space for a stack. And now you have this new phase of execution. And of course, this is like a hypothetical one, but this, you know, I'm kind of summarizing what I see often in bootloaders. You know, that will be ready, and so you have this phase where there's new regions of memory and new policies that you can add to that. After that, you'll have maybe be loading a target, and so suddenly you don't want it to write to other sensitive regions of memory, other than that region for the future substage that target image is being copied. And then there, you know, some success, in, you know, if it succeeded, some success substage where it's like ready to just jump into that next stage of boot. And this is, you don't need to read this, but like I'm just thinking how to label memory based on the substage. The left column would be like the initial bookkeeping substage where it just has access to registers, and then it gets into this next substage where there's some, you know, memory that's been enabled, and so you can start writing into more places. And then this final substage where, you know, it's actually, oh, that's not the final, but that's the loading one, where you still have these labels on there, but you can't necessarily write to certain regions because this is a different like type of substage than the previous one. The work I did to actually apply this type of policy to a bootloader resulted in this like big collaboration of tools, and I have the source code on GitHub. And there's this static analysis, data, then I use that to generate some tables that help with instrumentation and look for certain patterns in order for me to both study how the bootloader executes, and also to write a policy and enforce it, or to write a policy and see if the bootloader follows my expectations of how memory is being used. And with this particular tool set, I focused on writes because, region-based write access control are back. And I also, because I was focused on bootloaders, I wanted to mediate all the memory writes, even after relocation. So part of the tool suite is to keep track of what regions were relocated and, calculate offsets and so forth, so that it will move breakpoints, or, when it's tracking and it knows there's a relocation, it will start listening to that region, or it will know to add breakpoints depending on, the actual method of instrumentation. I do have a method where it inserts a breakpoint in every write instruction. So all those are, new ones are added when there's a relocation. So these tools is how I actually built a policy based on regions for a bootloader. And so one of the things I did is I needed to identify all the phases where it was relocating, when it was copying a big image for, like, say, a future substage for, maybe it's doing clearing out a region of memory, like zeroing it, or copying the target image into a region. My hypothesis was, when this happens, we'll see lots of memcopy write operations, by which I mean, a sequence of adjacent bytes are written in a tight loop. So if I were looking at just like the writes that happen, it would be, write A plus 1, write A plus 2, just sequentially and no other writes in between. And so I call these block write operations, and my tools will track that. And like what I contain in a block write operation is the address that was the instruction, the offset in the image, where the instruction lay in case it was relocated. We want to be able to sort of understand, like, if we look at the metadata of this image, we want to know we have the right one. Otherwise, if it's relocated, no metadata in that image will refer to the relocated address of the instruction. Then the destination of the write, the number of bytes that were written, and then I also keep track of where in the call stack it happens, which is helpful because I'm starting to think now about phases of operation. And where you are on the stack helps you understand the phase of operation, what the bootloader is trying to do. So you can distinguish between different mem copies, or mem copy zeros, so that's the BSS, but if you mem copy something else, I'm using the wrong one, but mem set 0. If you mem set something else, it's probably for a different purpose. So my corollary is that we should be able to use these block write operations to identify relocation phases, but also other sort of phases where large things are copied. And that's what I did. And if you're not gonna, there's nothing to help you understand this except for my voice. When I did the tracking, I found there was about 400,000 write operations for the U-Boot SPL on the BXM. And when I mapped that into block writes, I got 10,000 operations to sort of look through and figure out what they did, what they were for, what phase they could be assigned to. And here I sorted them all by size. The first column is the number of consecutive writes. And then it's I put the name. I then wrote the number of bytes at some certain address, and then I just put the instruction that was used to actually write the bytes. And this was ARM. So the first one is actually zeroing the BSS region. And I found other significant ones. Most of these were pretty significant. I just can't remember what they all are. But there's a bunch of MMC data read datas that I found, and I don't list them all because they're all the same size, but it's actually just reading the SD card in chunks of 5 to 12 bytes at a time and copying that into memory, and that was interesting. I found a region of relocation that I didn't know about, and it turns out there's a function called go to speed that is relocated, and it's for timing And it turns out it's never actually executed, so it must be something that's left over from some older code that they branched off of and never bothered to change. But that's like some relocation I didn't expect. And then there's, of course, a lot of like call stacks changes in here. But this really helped me kind of zoom down and figure out what different phases there are and what happens during those phases. And this is just for like a rough idea of the call graph that I simplified like a lot. The different colors, the yellows are what I ended up to define as a substage, like an entry point to a substage. So when start's entered, you're in like some initial substage. If you go from, if you go into low level in it, you're in another substage, et cetera, et cetera. And then I decided there's like a hang substage, and that's like a fail. There is a jump to image, which is sort of it succeeds, it gets to the next substage. And you can sort of have some policy enforcement there if you want. At the same time, I was tracing the call, making call trace of execution, and every call, function call and return, so that I can start saying, identifying the phase with the region of memory that was copied. And then in the end, like this is complex because this is actually what works on the U-Boot, and this is real, this is what I ended up with the phases of execution and the policy I wrote. And we can start seeing that beta is a bookkeeping phase, delta is a loading phase, and pi is a patching phase. And we can start seeing there's these different phases, and during some of these phases, there's different regions of memory. There's like important events. So after you can't read the name, blah blah blah, finish, this little go to speed relocated function is available. But it stops becoming available at the next substage because it gets copied over. And we can see when SRAM is like some external RAM, that's initialized. And you end up like seeing the progress of the bootloader and better understanding it in a way that you can't get from just reading the code. And in the end, I wanted to build something that looked like this. So the left side are the names of substages. The right sides are how I named like different memory regions. An edge between the two means writes are allowed to that during that substage to that region. So the policy I made was not just allow transitions between phases, but also what regions can be written during a particular phase. So when the phase clear BSS is executed, like only the BSS can be written and the stack. When it's copy clock code is where that weird relocation happens. Well, it should only write to the stack and to that little region that I call go to speed. So back to this email client that I had before. This potentially vulnerable email client. I mean, it's probably vulnerable. We can think about how it lives in memory. There's the application for it. There would be the library. Like let's just say there's some like library that handles the key. And like the key lives in its static data, the stack and the heap. And when it's authenticating, it needs to write to the key area. But when it's processing input, it shouldn't. But the nice thing, and this is where this project that I worked on called ELFbac comes in, is we realized that a lot of what happens in memory is based on how the file looks on disk. I mean, there's a bunch of ELF metadata, but in it, like I'm assuming that this is statically compiled, there is like a chunk, a region that's semantically, equivalent. All this, if we think at a coarse granularity at least. So there's like key, code for the application, data for the application, but then there's a different region that's data for the key library. And if you get that and start thinking about these ELF sections as regions, regions being types, types being policy, we have ELFbac, which is very related to my thesis work that worked on bootloaders, but this uses sections in the ELF binary as policy objects, and it has tools that allow you to define sections, new sections for policy objects. So you can have a fine granularity if you want. Always say that certain data live in certain sections in the ELF file, and it will be mapped that way, put onto the different pages, and the kernel will then be set up a page table for each phase of execution. So during the authentication phase, the page table will allow keys to be written. But during the process input phase, it does not have write access or read access to the keys. And so this ELFbac work has been championed by Sergey Bratis. Julian Banger wrote a kernel patch for x86. Maxwell Koo, who, I mean, he used to work at NARF, he wrote a patch for ARM, a kernel patch for ARM. And so, I have no idea what time it is, but some final thoughts. How can we trust software when it's so complex? And when these behavioral constraints we have on it don't directly encode this like high-level intention that we're most interested in. We do not want these keys to be written during that phase. It seems pretty important. I mean, a lot of the constraints we have now are very much looking at buffer overflows and code flow, integrity, and other things. And that is like important, and that definitely helps, like with large classes and tasks. But if we think about the software as like an entity upon itself that is different from all other software, well, not really, but if you just like look at the intentions of the software, we want to be able to really enforce those intentions. So with regions as types, we have this arbitrary object granularity in our policy, and we can intuitively encode some intended behavior with these phases and these regions. And I kind of like to think of it as a policy sweet spot. Maybe we'll find something even sweeter, but it's very much, it works on human like understanding because it's easily applied to modules. Different libraries are very like easily like their own region, and they often have a different trust level from the application itself. And reintroduce some of the terms that I'm trying to present and trying to champion a little. So the ELFbac is the region-based access control scheme that has more theoretical write-up, but also has tools that will actually build a policy and enforce a policy if you want to run it in GDB, that is. ELFbac is the kernel patches that uses the ELF file as a way to encode policy. And then Fiddle is the tools that I wrote for bootloaders, instrumenting them, and also for finding a policy, a region-based policy, and applying that as an enforcement, or just, if you want to see, you can have it not actually stop the code execution. You can just have it, label events when they happen that don't follow the policy. So, thank you for coming to this talk. You can find more details on ELFbac on my thesis at techregions.com and an ELFbac at elfbac.org, where you can get links to the source code. And I'd like to thank my research advisor, Sergey Bratis, who really couldn't do this work without. But I'm at NARF now, so he's not advising me. And thank you. I will post slides on Twitter, so if you follow me, you can get that. I'm sure someone else in the conference will retweet the link. I will add some references to it so you can see some of the work that I cited, including type state. So that's all I have. Do you have any questions? Okay, well, first person that asks questions gets the Steal This Computer Book 4.0. Okay.
So,
okay, Travis.
I'll take a free book. This idea of dividing the process into stages and then changing the permissions available at each point. Could this be easily ported to desktop software, sort of in like an OpenBSD pledge style?
So the question was, get me if I'm wrong, is this style of the regions, the policy objects, and the phases being enforced by that, can that be ported easily to desktop applications? That's your question?
Yes.
Okay. Yes, and that's, well, yes to asterisk. So ELFbac is exactly for that. It works on userland applications. It's tricky to work with now. Like, it really needs some library support to do well, and we just don't have like the the like developer power to get all that. But like if you had the right tools, I think it would be a lot easier. Right now we sort of have to reverse engineer some of libc to figure out how to include that in our policy. There's a lot of floating stuff and so forth that does unexpected things, and there's a lot of technical things we need to deal with, but I think the theory of it is sound. We applied this to, there was an OpenSSL bug, I think, and this was documented in an earlier talk, I think, at Black Hat. And so the ELFbac was used to kind of apply this policy based on regions over the existing OpenSSL library in order to not let that bug be invoked, or whatever the word is. So that was applied to existing code using this sort of, you should never be able to read this region of memory during this time of execution. And it was a very coarsely grained policy because it was focused specifically on that bug. But it worked. Anyone else? Yes, you the front.
Do you have we can find a policy and then verify or enforce the policy? Or once you detect the policy violation, you're terminating for just signal somehow that there is a policy violation. So that's why you can detect bugs, right?
Yeah, so the question was, by being able to write a policy and have that enforced or logged, you can detect bugs.
Related to that, does the code coverage come into play? Or how can you judge how much of the code is actually covered by testing it?
So how do you judge code coverage? I haven't done that, but I mean, I'm already running it in sort of a debugging environment, so you could probably compile in the code coverage libraries and build that in. I'd have to think a little bit more of how to integrate it all, but because I was looking at bootloaders, there's only so many paths through. But I think that could be done, and it seems like a really interesting use for it as like an actual debugging, quality control or something mechanism. Any other questions in the back?
Yeah, I was just trying to wrap my head around how you apply one of these policies. I mean, how much do you get for free based on what you can get out of elf analysis and things like that? Like the key example you gave, clearly you have to tell it that there's a key material somewhere, right? So what is, I guess at a high level, what does that kind of look like? How much work is that?
How much work is it to build a policy?
Well, and I guess I'm trying to understand a little bit about how it's applied, kind of at a high level.
And how it's applied. I mean, it also depends on the software too, and how it's laid out. So, I had a very specific idea of the type of policy I wanted to apply to a bootloader. So I was just looking for these big regions of memory being written. So there was this stage of me instrumenting it and getting that information. And I think I wrote a policy for that and kind of had to fix it multiple times because I'd find new things. I probably did like maybe 10 phases of like fixing up the policy to try to get something that worked. And then that's how I found all the stack changes. I didn't notice them before. So so it can be tricky. And I was working with existing code. I patched it a little bit to make it easier for me. So there's more of like when a new phase was entered, we knew it would never exit. So I had I changed a few calls so they didn't return, and that was just for a little insurance for me. But that was just for the theoretical side of knowing that being able to say it would only progress forward through this set of phases. But I think with more complex software, I wasn't the one that did the OpenSSL work. I think it was OpenSSL. So I'm not sure how long that took, but you certainly have to understand the software. If you're a developer for it, that's the idea of ELFbac is the developers can encode their intent at this higher granularity, and so they know their code a little better. If you're looking at some new code, it's certainly harder. Anyone else? I think that's time. All right, thank you for waking up so early.